Okay, we ended right here, I believe, right? I gave you a problem to do, and said if you can get these, and we kind of voted who got it, and so that's where we're going to pick up. So this problem is a little bit different than what we had been doing. We had been evaluating functions. This one gives you a table, and it asks you to answer the following questions. So you have the x, which is the input. You have f of x, which is the output. First question, does it represent a function? Yes or no? Okay, why? Each input, -2, goes to exactly one place. So you don't have like -2 appearing again over here. You don't have -1 appearing again. Each input only appears one time. So each input goes to exactly one place. So it is a function, yes. What is f of x the same as? Y. That's the y coordinate of the point. What is f of 2? -12. So you go to 2, spits out -12, right? Input, output. So the output is -12. What is f of -1? So -1 spits out 4, so you get 4 here. For what value of x does f of x equal 2? So this time we're looking on the right side. We're looking for f of x to be 2. That comes from an x value of 1. For what value of x does f of x equal -7.43? 0. So that comes from an x value of 0. F of 4 is 5. F of -1 equals 4 is the same as what ordered pair? So if you were to plot this as a point, you would do ordered pair. That's not an interval. Remember I talked about how there's a difference. Points and intervals look the same. So -1, 4. On a graph, that would mean -1 up 4. That would be a point, right? That's what that represents, that point on that graph. F of? Yes. So, well, look, this is f of x equals y, right? This f of thing is equal to y. Whatever this spits out is the y. This right here, -1, is the x that goes in. If the point 7,2 lies on the graph of f, express that point using function notation. So maybe this will clarify what we were just talking about. Here we'd write f of 7 equals 2. So we're going backwards from the point back to the functional notation. 7's the input, so it goes right here. 2 is the output, 2 is the y, so that's the function's value at 7. This clear? No questions? Okay. Now, instead of looking at a table of values, we actually have the graph. And when we say we have the graph, we mean these are actual points on the graph. Right? Those are actual points on the graph. This might be hard to do. Let's try it. Might have to zoom in here a little bit. What is f of 3? So what am I going to do? Go to 3 on the x-axis, 1, 2, 3, and then go up and find the y value that's on that blue graph. So what's the y value there? 4. Looks like it's over here at 4. So that's how high that point is. So the first one would be 4. Question? Okay, what about f of -3? You go to the right, 1, 2, 3, and you go look for the point, which is up a little bit. It actually looks like it's about 1 unit high. So 1. How about the next one? F of 0. Whoa, whoa, whoa. F of 0. So I don't move left or right, right? 0, stay there, and then go where? I have to go up to it, right? 1, 2, 3, 4. So since it's up, it's positive. Positive 4. Now, what's F of negative 4? So you go 1, 2, 3, 4 to the left, and you're actually, the blue dot's sitting right there. So the up and down value is just 0 because it's not up, it's not down, it's on the x-axis. So 0. F of negative 10. Negative 6, so go out negative 10, go down, try and find it, count, it looks like, is it negative 6? Yeah, I think we can all agree it's right there. Right there, negative 6. For what value of x does the function equal 3? So how are you doing that? You're going to 3 on the y-axis, looking to the left and seeing where it hits, which is right there, and then going straight down and grabbing the x value that came from. So you're finding the ordered pair that corresponds to that point right there. You see that? 3, it's 3 high. Where does it come from? X value of negative 1. For what value of x does the function equal 1? So this time we go up 1, and we look out. Do I hear a cat? Someone have a cat with them today? No? What does that look like to you? Does that look like 3? Looks like if you go up 1, it comes from where x is 3. So that would be 3. If we all agree. My graph will be a little easier to read than this, if it's on a test. So 3. Negative 3. Thank you. Did I say 3? Sorry. For what value of x does the function equal negative 3? So same thing. Go down negative 3. And then looking to the left and right, it's over here somewhere. Negative 7 is where it comes from. Where does the function's value equal 0? That means don't move up and down. Start looking for your graph left and right here. Where is it? Negative 4. And finally, what's f of 10? Yep. Now it's f of 10, so you're plugging 10 in, spitting out 4. All right. All right, some more practice. Are the following relations, are the following functions, find the domain and range. Is this one a function? Yes. X does not appear twice, right? No x value appears twice over here. Okay, what's the domain? All of these points over here, all of these numbers. How do we write a set of numbers? What do we use? The brace, yes. It's going to be hard for me to do this. A brace, and then negative 5, negative 4, 0, 1, 2, 3. Those are the inputs that are allowed here. What's the range? All the outputs, all the y values. So 7, 6, negative 8, 2, negative 13, and 4. You could put these in like descending order or like, lowest to highest, but it doesn't matter. It's, as long as you're listing out the values, you're good. How about the next one? Is this a domain? Is this a domain? Is this a function? No. Why not? Yeah, 1 goes to 2 different places, right? The repeating x value. So we are going to say no. So if you don't have a function, you cannot talk about a domain. When we talk about domains, we say the domain of a function is this. If it's not a function to start with, you can't have a domain. And the same thing with the range. The range of a function is the outputs of a function. If it's not a function, you can't talk about it. So as soon as it fails to be a function, the idea of domain and range we throw out. If your x, yes, because this is saying that 1 goes to 3, but this is saying 1 goes to 5. So which one is it? It's got to be 1, can't be both. But it is a relation. A relation is just any way of connecting numbers together. A function has that added requirement that no x value can repeat itself. How about the next one? Is this a function? Yes. What's the domain? With braces, right? 0, 1, 2, 3. And the range? 0, 1, 4, 9. Can anyone tell what that function does? Take 0 to 0, 1 to 1, 2 to 4, 3 to 9. What is it doing to the input? Squaring it. 3 squared is 9, 2 squared is 4, 1 squared is 1, 0 squared is 0. I'm just curious if you saw that. How about the next picture over here, number 4? Is that a function? Yes. What about the fact that 2 and 3 go to the same place? That doesn't matter, right? So this is good. Domain. 1, 2, 3. Range. 4 and 5. Number 5. So here's our graph. Goes like this. Is this a function? No? Why not? Doesn't have repeating x. How can you tell? There's a very simple way to check if a graph is a function or not. Anyone know what it is? The vertical line test. The vertical line test basically says that if you start drawing vertical lines, and it doesn't matter where you draw them, okay, just start drawing vertical lines. In order to be a function, you cannot hit the graph more than one time. Each line can only hit once, maximum. If you ever hit more than once, it's not a function. It's not a function. So do any of these lines hit the graph more than one time? No. Right? They each hit, like, here's once, here's once. So each individual line only hits one time. Does it make sense that if that didn't happen, it wouldn't be a function? Let me show you a picture. Let's say we had this over here. What if we had a graph that went like this? If I draw a vertical line that looks like this, how many times did I hit the graph there? I actually hit it 3 times. I hit here, here, and here. So if I said, go plug in this x value, it's going to have to spit out these 3 different things, right? That single x value, let's just say that that was 2 there. You go out x is 2, it spits out maybe what, 1, 0, and -2, let's say. That means that it goes to 3 different places. Impossible. It can't be a function that way. Make sense? So that's what we're hoping not to have. This is not a function. This one, on the other hand, passes the vertical line test, so it is a function. So the answer here was yes. What's the domain? So the domain's a little trickier here. What we're doing is we're looking for domain. We're saying what x's can be plugged in, and it actually spits something out. Okay, so our graph goes like this, right? So what is the first x value where things begin? You said the x value is -5. So corresponding to -5 straight down, that's the first time I get an output, isn't it? And then as I move across the x-axis from left to right, I'm always getting something out, right? Until I get to where? It looks like at 4 is where everything comes to an end. So would you agree that the domain looks like everything, not just single points anymore, everything between -5 and 4? So let me write this first. -5 to 4. Now what we need to determine is whether or not we actually get an output at -5 or not. So does it look like when we go to -5, we get an output? Yes, because that was a solid dot, wasn't it? That means there's output there. So that means I'm going to put a bracket on -5. How about at 4? Do I actually get an output at 4? No. Right before 4? Yes, but remember we talked about you can't get close. There's no closest number to 4. So how do we say stop at 4 without actually being 4? We use a parenthesis on the 4. This would be your domain. What about your range? I've kind of made a mess out of all this, haven't I? That's what's so good. I can just erase it all like that. How about your range? Range are the y values, right? So what you're going to do is, you know how we just looked at the graph and we moved from left to right on the x-axis and we said, where does it exist? For range, you're going to do the same thing, but instead we're going to move on the y-axis and look left and right. So looking from the bottom up, where does the graph actually start? And we're looking left and right here. At -4, it's where it starts. And as I move up, I've got graph, right? All the way until I get to 4. And that's where it stops. I look to the right. After 4, there's nothing. So -4 to 4. Do I actually have graph at -4? Look over here. Yes. Bracket. Do I have graph at +4 here? No, there's empty hole there. So I'm going to put parenthesis there. Just keep in mind, these are x values. And these are your y values. How about this one? Is it a function? So start drawing your vertical lines. You never hit it more than once, do you? So it is a function. What about domain? But I can't tell. Can you tell from yours if are those dots or arrows? Are those arrows? Okay, so let's assume that these are arrows right here at the end. What does the arrow represent? That it keeps doing that, right? It never stops. It just keeps doing that. So we're assuming the left side of this just keeps going up. The right side of this keeps going up. That means as it goes up, it spreads out, doesn't it? Slowly, but it spreads out. So if I go way out here and I look up, am I going to hit the graph somewhere over there? Yeah, way up there, right? If I go as far out as I want to the left, I go up, I should hit it eventually. Same thing with the right. If I go out to the right, go up, I'm going to hit. So we're saying that you can plug any x value in to the left, any x value to the right, everything in between. How do we say that? Everything. How do we say the whole number line? Not just infinity, you have to go -infinity to infinity. The whole thing. There was another one we could do. You could say all real numbers. Remember that? Double struck R. I would just stick to this convention right here, -infinity to infinity. Understand? Those are the x values that you're allowed to plug in. How about y values? So you start at the bottom, you're working your way up. There's no graph. As I look left and right, there's nothing until I get to 1. So 1 is where everything begins. And then as I move up, I look left and right, I'm hitting it. I've got graph, right? And I keep moving up, and I look left and right, and I've got graph. As far as I go, forever. So I need to say the range is everything. Bracket or parenthesis on 1? Bracket. The question is, do you actually achieve 1? Like, is your y value ever 1? Yes, like right at the bottom, right at that one spot, right? There's no hole there. But with infinity, you can never reach infinity. I mean, period. You can never get there. So always parenthesis. Questions? Is this one a function? Yes, passes the test, right? Draw your little vertical lines. So yes, it's a function. What's the domain? Those are arrows. Let's say these are arrows out here. Negative infinity to positive infinity. So you've always got picture, right? Left and right. You look to the left, you look up, there's stuff there. You go to the right, look up, it's there. Range is a little bit tricky. Any questions up to that point, though, on domain? Okay, how about down here? Do you ever reach like -2? Is that ever achieved by this function? No, it's hard to tell by the graph, but what's happening here is imagine that there's like a dotted line that goes out. These two arrows are getting closer to that dotted line, but never getting there. That's what they wanted you to see in this, but they didn't put the dotted lines. Same thing on this side. It's getting closer and closer without actually getting there. So when you're down here at like -2, you look left and right, you never get graph, right? When do you start getting graph? As I move up, when do I actually get graph? Right after 0. So here's the deal. At 0, if I look left, I'm on the dotted line. That graph never actually touches it. So I'm never going to actually hit it. Same thing on the right. Anyone know what these are called? These dotted lines that your graph goes toward? You've probably heard it before. An asymptote? No? Asymptote? Yeah, we'll talk about that more, but this is called a horizontal asymptote. So we have them here, and so we never actually get to it. So 0, do we ever actually get 0 out? We said no. Okay, how about after 0? Yes, until we get to where? 4, right? There's nothing past 4. Do we actually get 4? Yes. So how are we going to say this? Everything from 0 to 4, parenthesis on the 0 because I don't actually ever get 0, and then 4 bracket because I do actually achieve the 4. Are y'all doing okay with this? I was going to say my college algebra classes have trouble with this, but this is college algebra class. Are y'all understanding this? It's usually a light bulb thing. It's either like you've got it or you're like really way off on it. It's once it clicks, it's there, right? It's like, got it. Speaking of this type of function, I just want to kind of, you know how much I like to go off on tangents, and I hope y'all don't mind that too much. What function in the real world would actually look like that? Like what in the real world behaves like this? I mean, why would we ever want to study a function that behaves like that? So let me give you a quick example. First thing that comes to mind, have any of you ever seen that movie Fight Club? Long time ago, yeah? Fight? Yeah, I used to watch that movie all the time. Yeah, it was a long, I don't know. It's been a while. Okay, so if you've never seen it, then you can ignore, you won't know what I'm talking about. But one of my favorite quotes from that movie is the main character, I think. Yeah, it's the same character. So he says that on a long enough timeline, the survival rate for everything drops to 0. Okay, on a long enough timeline, the survival rate for everything drops to 0. So let's say that we have here time, and over here we have basically the survival rate, but let's look at it in terms of something that makes a little more sense to us. Probability you are alive. Now, this is not a perfect thing, all right? So just see if you agree with me on this or not. At time 0, let's say that's when you're born. And let's not get into like, when does life begin? And, okay, let's just say like, boom, pop out, doctor's like, that's the time, that's time 0, okay? At that point, we're assuming that you are alive, all right? So the probability that you are alive is 1, which is 100%, right? We know that a decimal, 1 gets turned into 100%. So there's a 100% you are alive the minute you were born, and they say that you're alive. Okay, after that, it's pretty much all downhill. You know, now we could say, you know, but if you get through the first, 6 weeks, then the odds are better that you're going to live. Just in general terms, would you agree that as your life goes on, the probability of you being alive starts to drop? You know, you're going to live to be 30? Maybe. You're going to live to be 50? Hopefully. You're going to live to be 80? Are you a man or a woman? You know? Or are you both? Well, hold on. Well, this is a whole different conversation we're not going to get into, right? I'm going to stop. Okay. So what about the probability that you'll live to 100? Could you live to 100? Okay, so do you see how this is dropping down? So maybe the chance that you'll live to be 100 years old, these are measured in years, maybe that probability, the height right there, is maybe it's 0.02, maybe it's 2%. Maybe 2% of Americans live to be 100. I don't know. 2% of humans. I don't know. I'm just making this stuff up. But what's the probability that you live to be 150? Well, I don't think anyone's ever lived that long, right? 150? 116? So I don't think anyone's ever lived to 150. Is it possible? Why not, right? I mean, it's not like at 100 all of a sudden it's like, that's it, right? I mean, there's no like, there's a lot of factors, right? Environmental, your own, there's so many things. No, just because no one's ever lived to 150 doesn't mean it can't happen. So I could continue this and get closer and closer to 0, couldn't I? So maybe the probability of living to be 100, we said, was like 2%, maybe. And maybe the probability of living to 150 is like 0.00002%. Who knows? Maybe it's even less. How about the probability of living to be 1,000? Can you say 0? If you round, yes. But just because something hasn't occurred doesn't mean it can't ever occur. That's one of the biggest things that mathematicians look at. I mean, if you look at it that way, if you believe that the Earth has been here for a couple of billion years, then you could argue that the sun has come up 4 billion times, or 4 billion years, whatever, how many days that is. So the sun has come up that many times, right? Does that mean the sun's going to come up tomorrow? I mean, just because something continues to happen does not mean that that's automatically guaranteeing the next thing's going to happen. So even though no one's lived to be 150, it could happen. Even though no one's lived to be 1,000, it could happen. But I would say that the probability of someone living to be 1,000 is probably, that probability is probably smaller than the probability of like you winning the lottery every day for the rest of your life and being struck by lightning every day for the rest of your life. I mean, could that happen? Could you win the lottery every day? So you go play the lottery, you win. Next day you go win. And as you're walking out of the store, you get hit by lightning every single time? I mean, that could happen. And you survive each lightning strike? Could it happen? It could. What's the probability of it happening? Infinitesimally small. That's why these functions that behave this way are important in probability and statistics and things like that, because we want functions that actually handle things that the probabilities drop off without actually ever going completely away. So you would not want to model this with a line, right? A line would not work here, because then you're going to cap it off. You're going to say no human can live past 100. That's it. That's the cap. All right. Sorry about that. Oh yeah, hey, the board function. So we're right now we are. Let's see, how bored are we right now? We are right about here. So we are working our way. All right, reaching that asymptote, right? Reaching that asymptote, getting them without actually getting completely bored to death. We reach it, right? Just barely. I lost my page. Sorry. Where am I? There it is. Well, no what? Not a function. Now look, I said you draw vertical lines. What if I draw this vertical line? I don't hit it more than once. The test says that every vertical line you draw can't hit more than once. So even though that one doesn't make it mess up, every one of them I draw has to obey it. And this one breaks the rule, doesn't it? I hit twice. No function, that means no domain, that means no range. Can't talk about it. Next one. Function? Yes. Domain. -3 to 3. What, there it is. Both brackets, good. Range? I heard it. -2. Looks like down here we hit -2, right? -2, and then all the way till we get up to 2, we've got something. Everything in between is filled in, left and right. So -2 to 2. I believe this is an arrow. Is that a function? Yes. What is its domain? Oops. Yeah, it looks like it's starting at -2. You got to kind of draw a line down. It looks like -2 is where things start to pick up. You've got function here. Over here, you don't have anything up and down. -2, and then the arrow represents this thing continuing like this. Does this look like that asymptote thing that I was talking about? Does it look like it's flattening out? It's kind of, you can't really tell, right? That's why we like to draw the dotted line. If it's going to get closer, we like to draw it. If we don't draw it, then we just assume it continues to go down, down, down forever like this. So if it goes over, are we gonna ever stop having x's to put in? We'll always have something down there, won't we? So we never stop. So -2 to infinity. I think y'all are getting this. I hope so. Range? Yeah, so I'm way down here, right? And I'm looking left. Left, there's nothing. But when I look to the right, that curve came down, didn't it? So I'm going to hit something over there. And I keep hitting as long as I'm going up until I get to where? 3, and that's where it stops. So -infinity to 3. Bracket on the 3 because I actually do achieve 3. Like it actually happens. I have a solid dot there. All right. Are we at homework yet? Oh. Or was that your homework? Did I accidentally do your homework? No, homework starts in a little while. All right. So this section's entitled Algebra of Functions. Algebra of Functions. What we've looked at so far is like, what is a function? How does it behave? Domain, range. We've talked about what happens when you plug things into a function, but we've always talked about just one function. Now what we're doing is we're looking at the algebra of functions, plural. And we're saying, what happens if you take two functions and you try and put them together? We have 4 algebraic operations. We call them the arithmetic or arithmetic of functions, plus, minus, multiply, divide, right? Add, subtract, multiply, divide. So this thing up here, algebra of functions, means using arithmetic on functions. Arithmetic meaning plus, minus, multiply, divide. So let's say that we're given 4 functions. First one's called f, second one's called g, then h, then k. Here they are. They're very different, right? These are very different functions. The first one's a line. Second one we'll learn is a parabola. This one is an absolute value function. This one is also a line. So we have these 4 functions. What we want to do is figure out what these things are. Well, I'll walk through this one and then we'll do the practice. So what is f of 4 over h of negative 7? So what does this mean? Plug 4 into the f function. So you go up here, you plug 4 in right here, which is what they do right here. H of negative 7 means plug negative 7 in right here for x into the h function. So when you do that, the absolute value of negative 7 is 7. After you figure out what each one of them is, this is a division symbol, right? So you just divide. Take that 8, divide by 7. Your answer is 8/7. So you have 2 functions separated by division, and then you just evaluate each function, then do the division. And you can do that for all 4 operations. You can do add, subtract, multiply, divide. So try this one. What's f of 0 plus g of negative 1? What's the operation between them? Addition. So we're just going to take whatever we get for f of 0, add it to g of negative 1. Tell me what f of 0 is. You're coming up here, you're replacing x with 0. 3 times 0 is 0. Take away 4, so negative 4. Then you're adding to that g of negative 1. So I need to go up and take a look at the g function. That you might have to do as scratch work on the side if you can't do it in your head. G of negative 1. I do 10, then negative 1 squared. This is very similar to what we ended class with last time, right? Where I give you a value, you plug it into the function, you make sure you don't mess it up on the calculator. What is that? All of it together. 5? I heard 5. 5? I heard, all right. Okay. 9? Should get 9 there. Nine. So we're going to come down here and we're going to say, all right, f of 0 was negative 4, and then g of negative 1 was 9, so we're adding that, and of course negative 4 plus 9 is 5. So the answer would be 5. G of negative 3, operation, multiplication. So we're going to have to multiply these 2 answers. So we're going to plug negative 3 into g and negative 3 into h. I'm going to write these down up here. Negative 3 into g, and I need negative 3 into h. So this is like scratch work I'm doing on the side. 10, negative 3 squared, plus 2 times negative 3 plus 1. What are you getting there for g of negative 3? 90, take away 6, add 1. You should get 85. What's h of negative 3? What do those 2 bars mean again? Those 2 bars? Absolute value. That just spits out the, whatever's plugged in just spits out the positive of whatever's there. So if I plug in negative 3, the absolute value of negative 3 is just positive 3. All right, so that's my scratch work. Now let me come down and answer this. G of negative 3 was, I already forgot. What was it? 85, okay. And then times the next one, which was 3. Was it? Yeah, 3. So what is that? 255. I think you could handle the rest. Plugging in. Yes. I plug in whatever's here. So here they wanted me to plug in negative 3. So I went up to G and I replaced the x with negative 3. That's here. And then I squared the negative 3, got a 9, multiplied by 10, got 90. Then this is negative 6. So 90 take away 6 is 84, and then add 1 is 85. Make sense? Yes, this negative 3 is replacing the x, yes. And then this one right here, it's replacing the x in the h function. Mm-hmm. Yep, yep. And they didn't both have to be negative 3. You know, you could have put 5 in here. It, you know, doesn't matter. They don't have to match. Like this one didn't match. 0 went into the f function, then negative 1 into this one. So some notation. If you ever want to add two functions together, you rewrite it this way. So keep in mind, when we wrote down this, what was the name of this function? What was the name of the function? F, right? F was the name. If I want you to take this f function and then take this function, which is g, if I want you to add them together, I have some special notation that I use to communicate that with you. Here's the notation I use. This f plus g is now the name of the function. See, it's always the thing in front of the parentheses with x. That's the name of the function, f plus g. And what it is exactly what you would think it is. It's take the f function, add the g function. If I want you to multiply two functions, what I do is just write f right next to g, fg. And that means take the two functions and multiply. So let's see if using that we can do the following. What does this mean? It means we're going to take f and plug in 0 plus g and plug in 0. That's what this notation means. Don't look at it as distributing or anything like that. This is purely notation. This means this. Now you have to figure out what those are. What's f of 0? We're looking at these two functions now. What's f of 0? So plug 0 in here, 0 in here, you get negative 4. Plus, what's g of 0? So that goes away, we have 1. Negative 4 plus 1? Negative 3. If you're running a business, you have cost, right? Like if I want to run a business, I have to pay, let's say I'm selling cell phone cases at the mall. That's my business. My costs are, I have to pay the rent for the building, the air conditioning cost, my employee costs, right? All these different things. That's my cost. Then I have profit, which is what? Money coming in? Money I'm making? And then I have this thing called revenue. Do y'all know the connection between these? Anyone in have any business background at all? What's that? No. Okay, so revenue is like what you're basically taking to the bank, right? At the end of it all, you have profit, money coming in, cost, money going out. Revenue is the difference between the two. Is that the way you see it? Okay. Or is it the other way? Is revenue the in and profit's what you take home? This is always confusing to students. So if you ever were confused on this, what can you do that couldn't be done 15 years ago? Google it, right? You could Google it, right? So I want you to see this. Let's Google revenue cost versus cost. That's probably too much information. Well, what did you think it was? Cost or profit, right? Minus cost. Let's see. Maybe it's not working out as easy, huh? As it looked. You believe this, though? It's on Google. It's got to be true, right? It's got to be true. So if we take this to be truth, then were you correct? You mixed the two. Okay, that's okay. I mean, it's not that big of a deal. What I'm trying to get you to see is let's look at this equation and let's move the cost to the other side. That's really what I wanted you to see from this. Because if profit, I'll put it this way, revenue equals, right? If I'm solving for revenue here, revenue is what? Profit plus cost? No, it's being subtracted. That's subtraction. So I add it to both sides. So then it's profit plus cost. Do y'all agree? Okay, so a lot of times in a business model, you'll have what's called your profit function. You'll have a way of determining your profit. If I sell X cases, I make this much money. That's my profit. And then cost is, well, you know, some function that represents your cost. And then if you add the two functions together, you get your revenue function. So that's all this operation is useful for, is combining functions together algebraically. And sometimes when you combine them, you get this new idea like revenue comes from cost and profit. All right, what about this next one? What's the difference between f plus g0 and fg0? You're multiplying. Isn't it the same values, though? Same values. So I'm going to plug in 0 to f times this time g of 0. We already know what those values are, don't we? -4 this time times 1, which is -4. So we got the same two values, but we multiplied them instead of adding them. What do you think this one means? Subtract. Which one goes first, G or F? G, because of the order, it's G of 0 minus F of 0. What was G of 0? 1, and we're taking away what was F of 0? -4. So that's actually going to become minus a negative, so plus. So 1 plus 4 is 5. Oh, homework, okay. So I guess you should be able to handle this homework. See how it goes, if you haven't already. I know this is a little early to take a break, but I think this is probably a good place to do it because we start this next section. There's not going to be a nice natural stopping point for us in about 15 minutes. So let's just take our break now. And we'll say at, what, 3:05 we'll come back? Okay. All right, moving right along here. We're still in the first test packet, but we're actually getting kind of close to the end. So let's see what we can get done here. All right. So topics, characteristics of graphs of linear functions. So most of what we're going to do right now, we're going to be dealing with lines. I'm sure a lot of you have seen lines graphed in the past, so a lot of this won't be new. But I know some of you haven't, so we'll take it kind of slow. The main things that we're going to be looking at initially are, with every line you have this idea of a slope, which is the pitch of the line. And that's going to be one of the main things we want to take away from this. And then with that slope, we're going to determine what's called the slope-intercept form of a line, meaning that every line can be written in this form. And so it's kind of like a standard form for writing a line. To start off, though, we need to make sure we understand the rectangular coordinate system. Okay, so each blank P in the rectangular coordinate system corresponds to a blank, blank, blank set of blank numbers. Okay, I'm going to try and fill this in. Each point P in the rectangular coordinate system corresponds to a what does it correspond to? What do you think? A blank, 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 x, y of blank numbers. Forget the blanks. Tell me about a point. When you're given a point, what are the things, what does it correspond to over here in a point? Okay. Whether or not that's what they want, that's the way I want you to look at it. A point is an ordered pair, right? X, Y of two numbers. I mean, think about a point, 4, 2. Is that the same as 2, 4? No. So order matters, right? That's what we call an ordered pair. And it corresponds to our X and our Y values. And it will always be two numbers, right? This will always be two numbers. That's how we determine what a point is. So how about this? What is the origin? It's the point 0, 0, right? If I graph it over here, it's this red dot. It's the origin. But it's actually where the x-axis and y-axis intersect, right? So it's the intersection of the number lines. The x-axis is a horizontal one. The y-axis is our vertical number line. Once we draw our rectangular coordinate system, we've partitioned a flat piece of paper into 4 different sections, and we call these quadrants. So we say the axes, or wait, sorry, the four regions formed by the x and y axis, and we use the following notation for it. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. So we usually use Roman numerals to represent the quadrants. Do y'all know which one's 1 and 2 and 3 and 4 here? No? Anyone know what 1 is? Top right. Then 2, top left. And it goes, which way is this? Counterclockwise. Why does it go counterclockwise? Anyone know why it goes counterclockwise? Just to confuse you, pretty much? No. There's a reason why, and if you had to take pre-cal, if you ever did, you would realize that when we measure angles, we always measure out the x-axis as being angle 0. And then as the angle opens, we open the angle counterclockwise, so the angle gets bigger. So you would want to naturally start in quadrant 1 and then go to quadrant 2 and then go to quadrant 3 and then back around to 4. That's why. The x-coordinate is the, what, first coordinate? In the ordered pair, the x-coordinate is the first coordinate. The y-coordinate is the second one. We already know this. What are intercepts? Intercepts. When we talk about an intercept, either one, right? So anytime you have an intercept, it's a point, okay? It is a point where the graph hits the axis. And it can be the x or the y. So when you draw a graph, if that graph hits the y-axis, it's called an intercept. If it hits the x-axis, it's called an intercept. If it hits the x-axis, it's called an x-intercept. If it hits the y-axis, it's called a y-intercept. Geometrically, when you talk about lines, the slope is a blank measure. Geometrically. So if you have a line, right, there's a line. When we talk about slope, we're talking kind of like a measurement of this right here, right? How much that pitches up. So geometrically, how could you, what is that a measure of? You'd probably an angle, right? But you would want to say the slope is an angle measure, angle measure. But let's just make angle, okay? All right, now how do we find the slope? Rise over run. You all heard that before? Rise over run? Okay, so if you're given 2 points, I will call the first point x1, y1, and I'll call the second point x2, y2. This is pretty standard notation. x1, y1 means the x-coordinate of the first point, the y-coordinate of the first point. Then the x-coordinate of the second point, y-coordinate of the second point. So given 2 points, someone gives you 2 points. Slope is equal to y2 minus y1 divided by x2 minus x1. Can you all see that's a minus there? Which is commonly referred to as rise over run. Rise being up and down, run being left and right. We'll come back to the other methods in a second. Let's just do these. So find the slope of the line that passes through the given points. So I'm just going to draw a quick picture so you get an idea here of what's happening. The first point is negative 7, 4. So I have a point that, and I'm just kind of real quickly drawing it. That's the point negative 7, 4. Y'all agree? To the left, 7, up 4. The next point is 8, 6. 1, 2, 3, 4, 5, 6, 7, 8. Up 6. About right there. There is a line that connects those 2 points, right? That's all you need to define a line is 2 points. We would like to know the measurement of that slope, the pitch. And to do that, we just need to figure out how much change in y there is and divide it by how much change in x there is, or the rise over run. So what I like to do is just label x1, y1, x2, y2. I just label these points. That way I can go straight to the formula. Did I put up here m? I didn't put m, did I? Come back up here. A lot of times, actually in most math books, we use the letter m to represent the slope of a line. So the slope is this calculation, which is rise over run, which is just m. So for us here, m is what? M is, what's y2? 6, take away y1, which is 4, divide that by x2, which is 8, take away negative 7. So you have to be careful with the double negative there, right? You're taking away a negative. So on top we get 2, the bottom we get 8 plus 7, 15. We can't reduce that, so that's our answer, 2/15. We do not convert that to a decimal. We leave it as a fraction. Now let's talk about what this means. What it means is if we start at this point, negative 7, 4, and we want to get to the next point on the line, we would rise by 2. We go up 1, 2, and we would run 15. And run means left and right. Positive 15 means to the right. So I now move 15 spots over to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. There. And that's where I would land, right there. So it just guides you getting one point to the next. Make sense? Now, inevitably, someone's going to do the same problem, and they're going to decide to be rebels, and they're going to call this x2, y2. They're going to call this one x1, y1. Is that coming out okay? Oh, yeah, that came out okay. If you label them the other way, opposite of what I did, are you going to get the same answer or not? Let's see. What's y2 for us now? 4, and I'm going to take away what? y1, 6, over x2, which is negative 7, and then take away 8. What is the top? Negative 2. What is the bottom? Negative 15. What's a negative divided by a negative? Positive. And you get the exact same slope. So it does not matter which way you do it, you'll get the same answer. Well, the thing is, how do you interpret this, though? I said to get from this point to this point, you go up 2, right 15. Up 2 because it was positive 2, and right 15 because it was positive 15. But how could I convince you that you could go backwards? Well, how about this? I tell you instead, use the negatives here on this. Don't simplify it. How do I get from here to here? I go down 2, 1, 2, right? Negative 2. And then how do I say to the left 15? Negative 15. 1, 2, 3, 4, 5, 6, all the way, and you get back to that one. So we're using the kind of the idea that 2 over 15 can be looked at as up to right 15, or you could look at it as down to left 15. It's the same thing. All right, see if you can do the next one on your own. See if you can find the slope of the next one. You don't need to draw a picture, just find the slope. I'll draw the picture while you're doing that. Oops. We there? What are you getting? Negative 3/4? All in favor? Yes. Was the negative up on the 3 or on the, was it on the 4? It was on the 4? Did anyone do it the other way around and get the negative on the top? No? Everyone labeled this one right here as x1, y1, and the other one is x2, y2. Okay. If you had done it the other way around, what you would have got is instead of 3 over negative 4, you would have got negative 3 over positive 4. But they are the same thing. Did we discuss that already with fractions, with the negative sign? I think we did, didn't we? If I have a fraction, 3 over negative 4, that's the same as negative 3 over positive 4. Those two are the same. The negative can be on the bottom or on the top, but it can't be up both at the same time. Here's your picture. Does everyone see that to get from one point to the next, I could go to the right? How much? Well, what's my rise? Sorry, to get down 3 and then right 4? Which of those fractions would it be to do this? Down 3, right 4. It'd be this one, right? Now, you could use this fraction if you want to go backwards, right? To get from here back to here, you would do up 3 and then to the right 4. That would be that one. Understand? Anytime you have a negative, it can be on the top or the bottom. So look, on this one, our slope was positive, wasn't it? And our line was kind of pitched up. Like if we read it like left to right, like a book. If you imagine that this is a roller coaster, right? Here you are on your little roller coaster, right? Standing on top of the car, like this, and your roller coaster is going, then you are going up, aren't you? Yes? Positive slopes have an upward pitch, if we're looking at it from left to right. Negative slopes pitch down, right? That's supposed to be a big old yelling, ah, okay? Right, going down. How about this one? What are you getting? You get 0 on top, right? Over, so you get 10 minus 10 over 25 minus 4. So you get 0 divided by 21. What's 0 divided by 21? 0. Can be either one of these. That says or. What does having a 0 slope look like? Flat line, right? We want to be careful. We don't want to say straight line, right? Because straight, that's a straight line. You know, flat line, horizontal line. So this is a horizontal line. Anytime the slope of a line is 0, it's horizontal. Try the next one. Two over 0, right? You getting 2 over 0? What's 2 divided by 0? Undefined. Undefined. Why? That's what you've been told, right? Can't divide by 0. Why? Because you've been told that, right? We don't care why. We don't care why? We don't care why. Can we talk about it? I mean, just for a minute? I mean, look at, whoa, wrong button. You've been told since the beginning of math that you can never divide by 0. Can never have 0 on the bottom. So I'm going to try and convince you as to why it doesn't make sense. This is in no way a proof or anything. It's just kind of like, yeah, now I see, like, it doesn't make sense to do that. If I say that I'm going to give you half of my pizza, all right? That means you start with what? A pizza. And with that pizza, I cut it into how many pieces? 2. So I'm going to cut it in 2 pieces. So the 2 right there is telling me how many pieces my pizza is going to be cut into, right? What is the 1 telling me? How many of those pieces that you get? So one of the 2 pieces would be that, 1 of 2 pieces, and that's half. Make sense? If I say 3/4, you get to have 3/4 of my pizza. I start out, right, with the pizza. I cut it into how many pieces this time? 4 pieces. So that comes from the 4 down here. How many of those do you get? You get 3 of those. 1, 2, 3. So you get some pizza, don't you? 3 out of 4 slices. All right, let's try this one. What about 0 over 4? Well, you start with the pizza. How many pieces am I going to cut it into? 4 pieces. That comes from down here, right? The 4 on the bottom. How many pieces do you get? None, so you don't get any pizza. So you get nothing, right? That's why 0 over 4 is 0, because you get nothing. I've got 4 pieces of pizza. You don't get any of them. Thank you. Thank you. Yes. Now let's try the big issue, the problem. Okay? I start out, I get a pizza. How many pieces am I going to cut it into? It's impossible to have 0 pieces. We're starting with a whole, right? A pizza. The denominator represents how many pieces I cut it into. I have 1 piece, don't I? I mean, the pizza is 1 piece. It's impossible to have no pieces. Does that make sense? And I'm supposed to take 4 of those no pieces. It doesn't make any sense at all if we follow the logic we had here. In all of these problems, we start with the pizza, and the denominator represents how many equal slices we get. We can't start with the pizza and then say cut it into 0 slices. It's 4 over 1. How many pieces do I get? You get 4. So 1 is how many pieces I'm going to cut this into. It is 1 piece, isn't it? So you get 4 of them. So you get 4 frickin' pizzas, right? 4 of those full pizzas. So the answer is 4. Does that make sense? It just doesn't make any sense in our, if you follow this logic for what a fraction is, to have 0 on the bottom. All right. It is what it is. But even though we have an undefined slope, we could still plot this, couldn't we? 3, 5 is this point, and 3, 7 is right above it, isn't it? And the line connecting those two then goes straight up and down. It's not a function. That is correct. But it is still a line, right? And it is a vertical line. So in summary, if your slope is positive, you're going up, right? Like a roller coaster. If your slope is negative, you're going down. If your slope is 0, you're horizontal. And if your slope is undefined, you are vertical. And that takes care of all the different scenarios that we could have with lines on a sheet of paper. This one just looks tedious, but I think I don't want to go through all these because it's going to take too much time. Let's look at this one because it has fractions. I know you enjoy fractions, and I'm all about making sure you have fun. So how about we label these? I like x1, y1, x2, y2. By the definition of slope, I need to take negative 7/6 and subtract from it what? That's y2. 5/6, 5/6. Take that entire thing and divide it by x2, which is 5/3, and subtract from that what? 2/3. Oh, look at those. They already have common denominators. I don't even have to get a common denominator here. So what are these two put together? Negative 7, take away 5. Negative 13, 12. Okay, I was going to say, hold on. Negative 12/6, which is just negative 2. Over, what's the bottom? 3/3. So you get negative 2 on top over 1 on the bottom. What's negative 2/1? Negative 2. So this can be a little tricky, all right? If somebody tells you the slope of a line is negative 2, we all need to understand that you can always rewrite negative 2 as what? Negative 2/1. People will get confused because they're like, okay, here's the slope, negative 2, and they're like, well, hold on, that's not rise over run. Where's the bottom? Well, it's always over 1. So you can always convert a nice integer into a fraction by just dividing by 1. You could also do 2 over negative 1, yes. Yes. This would be the answer, negative 2. What I'm saying is, if I tell you right now the slope of a line is 4, what's rise over run? Right? If I tell you the slope of a line, the slope of a line is 4. What's the rise over run? So you have to realize, okay, rise is 4, run is 1. So that's all I was trying to point out, is that anytime you're given a number, you can always look at it as that number over 1. There's your rise over run. Okay, let's move on. Possibilities, we already talked about this. Positive slope looks like this. Negative slope looks like this. Zero slope would be what? Horizontal line. And it could be moved around, but this is just to give us an idea of what's happening. Undefined slope, vertical line. I'm filling in what these are. We're going to describe these with the positive slope. We're going to talk about it as being an increasing line. So as you move from left to right, you're increasing. Do you all see that? Negative slope, you would be decreasing as you move left to right. Then horizontal, then vertical. Questions? Okay, hold on just a second. I'm going to do a quick swap of my mic battery. I've got to charge these this weekend. Just make sure this is picking up. All right. Now we get to what's called the slope-intercept form of a line. So this is a review. What is slope? What is the slope-intercept form of a line? When is an equation in that form? Or when an equation is in that form, what is the y-intercept? So let me first write down what the slope-intercept equation of a line is. Y equals mx plus b. That is the slope-intercept form of a line. Now, x is the input, y is the output. M is the what? M is the slope, so m is the slope. And of course, that's just a number, isn't it? It could be undefined, maybe, but we'll deal with that in a second. The question is, what's the b? The b is what we call the y-intercept. Now, the y-intercept, if you go back and look at when we're talking about intercepts of a graph, the y-intercept is the point on the y-axis that your line hits. So b is how high off the ground you are. Every line can be written in this form. What's great about it is that if someone writes it like this, you can automatically just look at it and know what the slope is and know what this point is. And if you know those two, it's very easy to graph them. So before we get to graphing, we need to make sure that we know how to get it into this form. So what is it that makes slope-intercept form unique? It's solved for y. Do you agree? Y, you've got y by itself. Right side is also simplified. And what I mean by that is that there are no parentheses, there's nothing being squared, everything on the right side is cleaned up. If you can do that, solve for y and clean the right side up, you are in slope-intercept form. And with that form, you can always identify the slope and the intercept. So let's take a look at this first one. When I say first one, I mean this. Can you get that into slope-intercept form? Yes? Okay, so we don't need to do these? What do? Divide everything by 2, right? Because you almost have y by itself here. So divide everything by 2. Why not subtract 2? Yeah, this is multiplication, right? So you're trying to undo multiplication, you come in with division. So divide the left side by 2. That means divide the right side, everything over here by 2. You'll be left with y equals 3 over 2x plus 4, because 8 divided by 2 is 4. And when we have 3x divided by 2, we just write it as 3 halves in front of x. You don't need to put the x on top. The x is just off to the sides. These are the same thing, or it means the same thing. All right, can you tell me what the slope of this line is? 3/2. Can you tell me what the y-intercept is? 4. So 3/2 is the number in front of x. You do not say that the slope is 3/2 x. It's the number in front of x. So just the 3/2. This y-intercept is the number by itself out here, which is 4. All right, let's do this one right here, number 2. What are we going to do to get y by itself? Divide everything by -3. -3, -3, -3. So what will that leave you with? Y equals -x plus 3, because negative over negative is positive. Any questions there? What's the slope? -1. Now that's coming from the -1 that's sitting in front of the x right there. Right, that's your m. How would you write that -1 as a fraction? Because right now it's not written as a fraction. You could write -1 over 1. How else could you write it? 1 over -1. Any of those would work. Okay? The answer is what's in yellow, but just keep in mind, that's what I was saying earlier, that when you have a number, you can always rewrite it as a fraction. What's the y-intercept? 3. Okay, how about the next one? 3. Is our y term by itself on this one? No, I need to start with that. Let's get the y term by itself. So let's take that 2x and let's move it to the other side. How do I do that? Subtract 2x on both sides. On the left side, they go away. I just get 3y. On the right side, I cannot put these together, right? This doesn't become like 13x, or they're not like terms. So I'll just write it in the order, what we call descending order. I put the x term before the constant. So -2x was here, then I had a positive 15. And then I heard it, you come through to get y by itself, divide both sides by 3 at this point. Everything gets divided by 3. Y is, -2/3 x plus 5. What's our slope? -2/3, and our y-intercept, 5. All right, and I'll let you do the remaining ones on your own, if you'd like. I don't see anything too tricky here. This one, you bring the 3x to the other side, you divide both sides by -3. This one, you bring the 2x to the other side, you divide both sides by 2. This one, divide everything by -1. Oh, I didn't see those. Ugh. Okay, more of the same. Give me just a second, if you don't mind. Okay. 342. Let's take a look at 12. On this one, I need to get the y by itself first. So how do we get that 1/2 x out of there? Subtract it. -1/2 x minus 1/2 x over here. On the left side, it goes away, which leaves you with the 2y. On the right side, what am I gonna write down here? -1/2 x plus 6. Good. Then divide by 2, and that's why I wanted to show you this one. What does it mean to divide -1/2 by 2? See, I can do 2 here, I do 2 here, I do 2 here. I think 6 divided by 2 everyone's pretty comfortable with. But what's -1/2 divided by 2? -1/4? Is it, do the 2's cancel? You see how this is a little tricky? So I think I'll talk about it over here on the side. When you say negative 1/2 and you are dividing it by 2, the division that you're coming in here with is the big division. So that's our big division bar. We are not creating 2 over 2 and figuring out what that is first. We have to leave the negative 1/2 intact and then rewrite the 2 here as a fraction, 2 over 1. So that's the same problem? Yes? Now, what does division mean? Multiplication of the reciprocal. So this turns into negative 1/2 times what fraction? 1/2. Because this one comes and flips. And now when you multiply 2 fractions, you go straight across, don't you? Negative 1 over 4. So just be careful on that. I wouldn't want that to get you in trouble there. Negative 1/4 x plus 3. Questions? What's our slope here? Negative 1/4. What's our y-intercept? 3. Okay, we're getting there. I think it's time to do a little practice here. I need to show you how to do maybe one or two of these. I want you to graph these. Okay, so let me do a couple examples, and then I'm going to let you work on a couple together, just to kind of get your blood flowing a little bit. So let's say I wanted you to graph y equals negative 3x plus 7. First, you have to know that this is a line, right? You have to know that that's a line. And you know that because, how? How do you know that that's a line? Just because you've seen enough of them, or what? It's in slope-intercept form, right? I mean, it was given to you like that. But the way you indicate that you have a line is pretty simple. You have an equation. You have 2 variables, x and y, and both of them are raised to the first power. If you have x to the first, y to the first, and an equal sign, you have a line. Now, if it's in this form y equals mx plus b, if it looks like that, then you're ready to graph it right now. So what is the procedure to graph this? Identify slope and y-intercept. Put them down. Write them down. What's the slope? Negative 3. Can you write that as a fraction? Negative 3 over 1. Is that the only way? Careful, you flipped it. Yeah, 3 over negative 1. So you can use this slope or this slope. It's up to you. You get to make the decision. What about the y-intercept? What is it? 7. Now, here's how we do it. We draw a graph. The slope tells us how to get from one point to the next, doesn't it? Rise over run. But we need a point to start at. What point do we know exists on this graph for sure? At 7 on the y-axis, right? So if I go up 7, 1, 2, 3, 4, 5, 6, 7, right here, I can draw a point. That point definitely lives on my graph. Now take me to another point. Where do you want me to go from here? I can go up 3 to 10. Which way over? Left 1. So you would be using this to do that, right? That's one option. Another option would be to use this, which would tell you what? Drop 3 down and then move right 1. Let's do both. You're going to see they create the same line. So if I drop 3 down, I'll highlight it. I drop 1. Oh, that didn't work. Use a different color. If I drop down 1, 2, 3, and then move to the right, how much? 1, I'd be there. But if I chose to do it the other way and go up 3, 1, 2, 3, and then to the left 1, I'd be here. Either way I go, damn it, I missed it. Either way, I draw the same line, don't I? Okay. So this is what I want you to do for the following problems that I'm going to give you, all right? I want you to go through, find the slope and y-intercept, and graph them. And why don't we make this worth your while? I'm going to give you some problems from the homework, so that way you're kind of doing something productive. Where does that homework start? Okay, I'm looking at, this is page 49. On page 49, they ask you to find the slope and y-intercept by using the slope-intercept form equation line. If necessary, solve for y first. So put it in this form. So why don't we do three, 4, 6, 10, and 11. So for those problems right now, I want you to get it into the form, figure out what M is, what B is, and then graph it. And your graph does not have to be perfect. You saw my graph, right? You just don't want it to be like on your page. You don't want it to be like super tiny, like really small, like a little line like that where no one can tell what the heck it is. I mean, take up a little space, draw out your dashes, label things. All right, let's see how much you can get done here. We have, what, 5 problems? You can help each other out.